My name is Yue Hao. I'm a PhD student in computer science at George Mason University. So my topic is computational laser forming of origami of convex surfaces. So laser origami is a general term for for using a laser to fold 2D sheets into 3D structures. Here we show some related work using different folding mechanisms. The first one is polymer softening, where the polymer is heated by the laser and folded down 90 degrees due to gravity. The second is the release of pre-strained films, where the two layers of different materials are involved. And the third one is laser forming, the technique we used here. Laser forming is an established metalworking technology that evolved in the 1980s. In laser forming, a laser is used to selectively heat the metal sheets to create plastic thermal stresses for controlled deformation or folding. Comparing 3D printing with laser forming, the cost of 3D printing can be very high depending on the material, resolution, and geometry. People have been using lasers for cutting various 2D geometries accurately and efficiently at low cost. Laser forming makes it possible to fold the metal sheets without any modification to the hardware at no additional cost. So there are many slicers available for 3D printing. However, no such software has been researched or developed for laser forming. Our ultimate goal is to create computational tools for laser forming equivalent to slicers for 3D printing. In current practice, most folding in laser origami has been limited to simple designs, manual placement folds. Our work is the first that procedurally generate laser formable patterns and folding instructions to guide a low-cost laser cutter to cut and fold a sheet into complex 3D shapes. One of the most important methods in laser origami laser forming is known as temperature gradient mechanism, or TGM. In TGM, the laser is rapidly scanned across the surface, creating a vertical temperature gradient through the metal thickness. Initially, the top expands and relative to the colder side of the material and push against the expansion, resulting in compressive plastic strains. When the workpiece subsequently allowed to cool, the initial expansion disappears, but the compressive plastic strains remain in the material, resulting in bending back towards the laser source. The time cost for cooling is much longer than heating caused by the laser passes, resulting in the thermal constraint that time delays must be allowed between laser passes. Given the number of laser passes scanning through a crease, we can fold the crease up to 90 degrees. The data plots shown here are measurements taken from 75 micrometer thick stainless steel. There is also a buckling mechanism where the laser is scanned more slowly to allow the heat to reach all the way through the thickness of the material, which results in downward folding. However, such mechanism is not mature, as it is necessary to control the direction through the additional folds, such as pre-strain in the material. In this work, we focus on TGM alone, which enables us to laser form a variety of convex surfaces. The laser marker with a single laser head can translate on a 2D plane, z equals 1, and can only emit laser vertically downward and focus on z equals 0 plane, which causes what we call the work plane constraint. There's also visibility constraint that existing folded structure must not block the visibility between a crease line and the laser, as the dashed line shown in the picture. And of course, there's a rigidity constraint that the 2D pattern must not self-intersection during the folding process. Based on our modeling, we can summarize our laser forming problem as fabricating 3D shape using 2D pattern and 2D motion, subject to these constraints. Here we give an overview of the end-to-end fabrication process developed in this work. Given a 3D mesh of the target structure, we unfold and optimize the mesh into 2D pattern. Then we plan the folding motion, which brings the 2D shape to the 3D under the constraints of laser forming. The motion is also simulated and verified. Based on the 3D folding motion, we generate the 2D laser path and store the laser passes in time sequence in a SVG file. We also built a software called LoCAD to customize the laser power and time delay settings and deploy the settings to the hardware. LoCAD gave us the freedom to adjust the settings such as the laser power and delay time based on the substrate properties and the hardware environment without redesigning the pattern or replanning the folding motion in the previous steps. Finally, we send the result for fabrication using our laser marker. So there are many ways to unfold 3D models into 2D patterns. So here's two. The first one is called the polyhedral net unfolding, which cuts several edges, but the remaining is still a connected component. The other one is called the rigid origami, which generated by adding tuck faces between the triangle faces in the original mesh so that the 3D mesh can be flattened. Here we choose the polyhedral net because the tuck neighboring face need to be folded in 180 degrees, which is not achievable due to the visibility constraints. In addition, during folding, the rigid origami is subject to closure constraints, meaning that the several creases must be folded together. For the model, like a single vertex shown here, the laser need to focus on a slope with z greater than 0, which violates the work plane constraint. For polyhedral nets, creases can be folded independently in a sequence. In order to plan a folding motion that satisfies the constraints, we propose a simple folding strategy called outside-in folding. Here is an example of the cube model and its polyhedral net. Because polyhedral nets are tree structures, shown as the dual graph in red, we can always assign a face as the root of the tree and assign child and parent relationships using breadth first search or depth first search from the root face. Then the outside-in folding strategy simply requires the child face to be folded into 3D before any of the parent faces to be folded. Subsequently, the leaf of the net will be folded first, and the root face will remain in the work plane. For example, here we start with the blue crease to fold the leaf face. Another leaf face folded. We fold the parent crease shown in blue. Notice there are 3 leaf faces here, and there's still decisions to be made which leaf face to be folded, or first, or just fold them at the same time. Sometimes it may cause self-collisions or wrong folding sequence. We use a probabilistic motion planner to help us resolve the collisions. Due to the visibility constraints, if a net has more than one crease line whose dihedral angle is less than pi/2, the net is not laser formable, only using TGM. This is because one of the face incident to such crease will occlude the line of sight from above if the other face is fixed at work plane. Therefore, the only way to fold such crease will require both incident faces to fold, but make sure that they fold less than pi/2. Such crease must only be folded at the end of the folding process. We can only afford to have one crease line with acute dihedral angle. Here's another example of model similar to cube and 3 of its unfoldings. Only the rightmost one is TGM laser formable. This observation indicates that if we might need to exhaust all the unfoldings before we can conclude a certain structure is not TGM laser formable. The laser forming technology fabricating 3D models by ultimately moving a control point following a path in a 2D plane. We only have one laser head, however, there are multiple creases folding at the same speed. In order to fold multiple creases in parallel, we need a scheduling strategy, making it act as if we have multiple laser heads. We call this strategy fake parallelization. As shown in this 10% speed payback simulation, when a crease is cooling down, the laser switch to work on another crease. For some result, we fabricated a curved surface. The cuts are shown in rasterized areas around the boundaries. Instead of cutting the entire boundary, and before folding, we iteratively cut and fold to ensure the stability of the structure and so that the heat can escape from the structure. This causes failure as some parts of the structure are not fully separated from the substrate. near the creases. To solve this problem, we extend the boundary of the cut and make a small overlapping between the neighboring hatches. These results show our fabricated the same Sinuous antenna models in different tessellations from 40 triangular faces to 227 triangular faces. The fabrication time ranges between 4 and 5 minutes for all models. This is because as the number of crease line increases, the folding angle and the number of laser passes decrease for each crease line, which means laser forming can fabricate high-resolution tessellations and smooth curvature without compromising efficiency. A low-cost 20-watt 1064 nanometer fiber laser marker and a substrate of 75 micrometer thick stainless steel are used in our experiment. The fabrication process shown here in the video is speed up 4 times. The bright spark you see in the video is generated by laser cutting when the laser beam is set at a full 20 watts power. However, for folding, only 10% of the laser power is needed, as shown in the dimmer sparks. And as we have mentioned previously, instead of cutting the entire boundary before folding, we iteratively cut and fold. This ensures the structure remain attached in the substrate during the fabrication process until the last face is cut out. The laser marker here actually using a mirror to control the laser path, which we use a slightly different implementation for the visibility check of the laser marker. In conclusion, this paper presents a computational method that can produce TGM laser formable structures of convex surfaces. Our method increased the complexity of the laser forming far more than the manual design of structures that typically contains only a few folds. For the first time, an end-to-end laser forming pipeline is presented, and as G-code and slicers in 3D printing, this framework can pave the groundwork for eventually transform laser forming and laser origami to practical method for low-cost, customizable fabrication. Laser origami has many potential applications such as metal antennas, as shown in this work, 3D circuits, etc., that will complement the applications of existing 3D printing technology. The foldable structure discussed here are limited by the hardware capacities. Our discussion has been focused on laser cutter with vertical laser directly from above. We can fabricate far more complex structures if the laser rays can be sent below the sheet. An example of such structure is shown in this video. Unfortunately, such laser cutter with dual laser head is not available to us now. Alternatively, we're working on using a rotary to rotate the sheet 180 degrees to allow the laser to fold the backside of the substrate. So this concludes our work. For more details, please visit our website. Thank you.
One quick question.